Welcome back to my channel. I am your academic coach, Yuhyun. Today it's day 3 of AP Physics 1. Today I'm going to talk about speed versus velocity, and I'm going to talk about average velocity versus instantaneous velocity and how to calculate velocity. Let's start from average speed and average velocity. Most of you have already learned what's an average speed and how to calculate it in your math class. Either in Algebra 1 or Algebra 2, you've solved a lot of math questions that ask you to calculate speed when you are given a distance and time. So, average speed is as simple as distance divided by time interval. Here, I use the term time interval instead of just time to represent that it's a period of time that takes for an object to move across a distance. For example, if an object moves from point A to point B and then it started moving at 3.0 seconds and then it arrived at point B at, let's say, 13.0 seconds, then here for time interval, I'm not going to plug in 13 seconds or 3.0 seconds. That specific time for the moment does not really matter. What matters is how many seconds it takes for this amount of distance, which is T2 minus T1. 10.0 seconds. And again, in physics, delta of a physics quantity or change in a physics quantity is always final value minus initial value. That's why I subtracted T1 from T2. And as you know, since distance is a scalar quantity, when you divide a scalar quantity by another scalar quantity, which is just a numerical value, then of course you still get a scalar quantity. So average speed is also a scalar quantity. On the other hand, average velocity is a vector quantity because it is displacement divided by time interval, and displacement is a vector quantity. And you've learned that when you multiply a vector by a numerical value or a scalar, it always gives you another vector quantity. So when you divide a vector quantity by a scalar quantity, that still gives you vector quantity. Remember that I used the term of average speed and average velocity instead of just saying speed or velocity. And the reason is because I don't know what would be the speed or velocity at a very specific moment. I was just using a whole chunk of time and a whole chunk of distance or displacement to quickly calculate or give an estimation on how fast the object was moving for that period of time. But there's a problem of using those terms. Here we have an example of a car that moves around a circular path and it takes approximately 4 seconds. So if I want to calculate the average speed, then what happens is I'm going to take the total distance and divide it by time interval. The total distance would be the circumference of this circle, which is 2 pi r. And when I divide it by 4.0 seconds, then I will get 1 half pi times radius. And the unit is meters per second. And once I know the radius, I can just plug in the number for radius in this formula. But what if I want to calculate average velocity? Well, this is the initial position. But at the same time, that's also a final position because the car was back to the starting point. That means delta x final minus x initial, is equal to 0. So for average velocity, which is delta x over delta t, it's going to give me 0 divided by 4.0 seconds, which is 0 meters per second, which does not really reflect what's going on in reality. In reality, the car was actually moving. But when I use the average velocity formula, it gives me the answer that the car was not moving for 4 seconds. So that would be the problem of using the term average speed or average velocity. So that's why we prefer to use instantaneous velocity or speed whenever we calculate how fast an object is moving. So if you see the term of just speed or just velocity, they automatically refer to instantaneous speed or instantaneous velocity, which is how fast an object is moving at a specific moment instead of taking an average value. And instantaneous velocity's magnitude is always instantaneous speed. It's basically speed plus direction. And how we measure speed or velocity in reality or in physics lab is through motion detectors. There are two types of motion detectors that high school physics lab has. One of them is this motion detector that use ultrasound wave. How it works is it emits an ultrasound wave which cannot be heard by human beings towards an object. So once the ultrasound wave hits the object, it's going to be reflected back. And once it's reflected back to the motion detector, it's going to measure the time from the very beginning when it just emits the ultrasound wave until it receives the reflected wave. And based on that time, it can calculate how far the object is from the motion detector. And it's not going to calculate the distance only once. It's going to consistently calculate how far, it's going to consistently measure how far the object is. And based on that, it can measure the distance between the detector and the object and how fast the object is moving. And another motion detector that you might see in high school physics lab is called photogate. And photogate uses infrared wave to detect the motion of an object. How it works is now you see that it looks like a bridge. It looks like that upside down U shape, and from one end to the other end, it's gonna shoot an infrared wave. And what you're gonna do is you are gonna set up this photo gate above the track, above the linear track the object is falling through. And you are gonna make sure that the object will pass through the gate between these two parallel parts. So what's gonna happen is once the object starts moving and it passes through the photo gate, the infrared wave between these two gates will be interfered. So before the object is moving, you can always detect the infrared. But once the object's one end started crossing the photo gate, it cannot detect it anymore. And it cannot detect that infrared wave until the whole object passes through a photo gate. And based on for how many milliseconds or how many nanoseconds the infrared wave is not detected, then it can calculate how fast the object was moving. So that was how we can use some tools in lab to calculate instantaneous speed or velocity. But what about mathematical way? Because we are not going to use those tools when we solve some physics problems on paper. So on paper, we are going to use this formula. Here, the velocity automatically means instantaneous velocity is the limit of delta x displacement divided by delta t as delta t approaches zero. If you have learned calculus or if you're taking calculus right now, then you would know what that limit sign is. If you're taking algebra 2 or pre-calculus, then you might not know. But no worries, I'm going to explain that what it means. So let's go back to this example. So at the very beginning, what we did was we took the starting point as x initial, and then we also took the same starting point as x final. And then we took the time interval of 4.0 seconds. And that gave us average velocity of zero. And we do not want that. So instead of that, what I'm going to do is I'm going to take a much smaller time period. So for example, I'm going to take delta t to be 1.0 seconds. Then my x initial will be at this point. My x final will be around this point. Because from 0 second to 1 second, the car has moved from this position to this position. Then what happens is when I connect x initial and x final, then I will get delta x displacement. So for this time interval, then the velocity would be equal to delta x divided by delta t. And this means that my velocity will be a vector pointing in the same direction as delta x. I know that this is still not as accurate as I want because at the very beginning, the car was moving towards this direction instead of moving towards the right bottom corner. We can fix that by taking even smaller time interval. This time, I'm going to take delta t is equal to zero point 0.1 seconds. Then x initial is still at the starting position, but x final will be at a point very close to x initial. This is x final. And when I connect these 2 points and put an arrow to the right, this represents displacement, delta x. Then this time, velocity would be equal to delta x divided by delta t, which is zero point 0.1 seconds. And again, this means that velocity will point in the same direction as delta x. So we're going to repeat this process all the way until delta t approaches 0, or delta t is a very, very, very small time increment. Let's say 0.001 seconds. Then what you will see is x initial and x final will be 2 points that are so close to each other that they just almost overlap. Then the delta x displacement between these 2 points can be represented using a line that is tangent to this circle. And when you divide that delta x vector using delta t, which is a very small time interval, then you will get that v velocity points in the same direction, which is a line tangent to the circle. So this is how we calculate the instantaneous velocity. Now let's do a quick quiz to make sure that you've understood everything I just explained. Question number 1. You are driving home from school at 95 kilometers per hour for 130 kilometers. Then you slow down to 65 kilometers per hour. You arrive home after driving 3 hours and 20 minutes in total. How far is your hometown from school, and what was your average speed? So, once you see a physics question, the very first step you do should be visualize it by drawing a diagram or by representing the motion. And it's asking, how far is your hometown from school? It's very obvious that we're missing the distance for the second part. So now I have separated into the first part and the second part. I know the distance for the first part, but not the second part. But what we know is we are given the total amount of time. Okay, so now think about it. To calculate this distance, we are going to apply the formula of average speed is equal to distance divided by time. So distance is equal to average speed multiplied by time delta t. And here, what we are missing is we are missing delta t. We need to find the time for the second part. And we are given the time for the total. Delta t total is 3 hours and 20 minutes. If I convert that into hours only, then it will be 3 and 1/3 hours. And we can calculate the time it took for the first part, again, by applying the formula of average speed is equal to distance divided by time. So time is equal to distance divided by average speed. So 130 kilometers divided by 95 kilometers per hour. And that is 1.37 hours. So now I know that delta T2 would be equal to delta T total minus delta T1. So 3 and 1/3 hours minus 1.37 hours. That is 1.96 hours. So now we know that the time it took for the second part. Then I can calculate the total, I can calculate the distance for the second part. 65 kilometers per hour multiplied by 1.96 hours. And that is equal to 128 kilometers. So the total distance would be distance for part 1 plus distance for part 2. That's 130 plus 128. And that is 258 kilometers. And now we need to find the average speed for that entire trip from home to school. And again, we are going to use the formula of average speed is equal to the total distance divided by time interval. So total distance is now 258 kilometers, and the total amount of time is 3 hours and 20 minutes. So 3 and one third. And that is 77.4 kilometers per hour. The next question, question number 2. A person jogs 8 complete laps around a quarter-mile track in a total time of 12.5 minutes. Calculate the average speed and average velocity. So this seems like a really easy question. So a quarter-mile track, this is how it looks, and each lap would be 1/4 mile. And if this person jogs 8 complete laps, that means that their total distance traveled would be equal to 8 times 1/4 miles, which is 2 miles. The problem is it wants us to calculate speed and velocity in terms of meters per second. So we need to convert miles into meters. So that would be 2 miles multiplied by 1,600 meters per mile. So that would be 3,200 meters. And total amount of time is 12.5 minutes. And again, we need to convert that into seconds. So I'm going to multiply that by 60 seconds per minute, which is 750 seconds. So now I have the total distance and I have the time interval. I can calculate average speed. Average speed, which is distance divided by time interval, would be 3,200 meters divided by 750 seconds. That is 4.3 meters per second. What about average velocity? The initial position is equal to final position. This means delta x displacement is equal to 0. And that means that average velocity, delta v, should also be equal to 0. Next, question number 3. An airplane travels 3,100 kilometers at a speed of 790 kilometers per hour, and then encounters a tailwind that boosts its speed to 990 kilometers per hour for the next 2,800 kilometers. What was the total time for the trip? And what was the average speed of the plane for this trip? The first step for such a question would be visualizing, and it's asking us to find a total time for the trip. The only equation we have learned for now would be average speed is equal to distance divided by time. To find time, we should rewrite that as delta t is equal to distance divided by average speed. And for these two separate parts, we need to calculate the time interval separately because they have different average speed and different distance. Delta T1 would be equal to 3,100 kilometers divided by 790. And that gives us 3.92 hours. For the second part, delta T is equal to 2,700 kilometers divided by 990 kilometers per hour. And that gives us 2.73 hours. So delta T total is T1 plus T2, 6.65 hours. Next, to find the average speed of the plane, then we are going to again use that formula of average speed is equal to distance divided by time interval. And here the total distance d is equal to distance for part 1 plus distance for part 2. So 3,100 plus 2,800, which is 5,900 kilometers. And we already have the total amount of time, 6.65 hours. So average speed would be equal to 5,900 kilometers divided by 6.65 hours, which is 887 kilometers per hour. This is the average speed for the plane for the entire trip. Next question. A bowling ball traveling with constant speed hits the pins at the end of a bowling lane, 16.5 meters long. The bowler hears the sound of the ball hitting the pins 2.5 seconds after the ball is released from his hands. What is the speed of the ball? The speed of sound is 340 meters per second. How we human beings hear the sound is the sound wave travels from an object towards all the way until it reaches our ears. That's how we hear the sounds. So there is actually a little bit of time difference between when a crash actually happens until we actually hear the sound. Let's say here is the pin, and here we have the bowler standing there. And the ball was moving at a certain speed, but we don't know that. And once it hits the pin, the sound wave was traveling back. So here, 2.5 seconds after the ball is released. So that means that after the ball was released, it traveled all the way towards the pin. And then here, the sound wave was created, and the sound wave traveled all the way back to the bowler. And that total amount of time was 2.5 seconds. The unknown variable would be the speed of the ball. Average speed is equal to 16.5 meters divided by delta t. But still, I don't know the delta t. So let me use delta t ball to represent the time it takes for a bowling ball to uh, go from here all the way towards the pin. And next, I can have another equation for the sound wave. S is equal to d divided by delta t. And this time, I know that average speed for a sound wave is 340 meters per second. That's equal to 16.5 meters divided by delta t sound. And delta t sound represents the amount of time it took for a sound wave to go from pin all the way back to the bowler. The next, what I know is for these two time intervals, delta t ball and delta t sound, they add up to 2.5 seconds. Our equations look a little bit messy. If I drop all of the units and just simplifies it to just unknown variable and number, then this is the system of equations that I get. And here we have three equations. The very first equation that I can solve would be this one, because in this equation, there is only one unknown variable, Ts. Ts would be equal to 16.5 over 340, which is equal to 0.0485 seconds. Once I know that, I can use this equation to calculate Tb. Tb would be equal to 2.5 minus Ts. 2.4515 seconds. And once I have Tb, I will be able to plug that in into this equation to find S. S is equal to 16.5 over Tb, 6.73 meters per second. In AP Physics 1, you wouldn't be tested on such questions, which makes the average velocity and speed so complicated. But these are the questions that actually help you to understand how to apply that really simple equation of S is equal to d divided by delta t into the real life example. Relative velocity is the velocity of an object from an observer's perspective. And often we use V observed is equal to V actual minus V observer to represent relative velocity. Problem arises because it can be a little bit confusing when there are multiple moving objects. So instead of that, let's try to use our second formula. VAB is equal to VA minus VB. What it means by VAB is the velocity of object A relative to object B. And VA represent velocity of object A relative to the ground. VB represents velocity of B relative to the ground. For this person standing still, let's use V person to represent its velocity. And for this kid riding the bike, let's use VB to represent its velocity. Then, from that person's perspective, the biker was moving at VBP, which is VB minus VP. 3 minus 0. 3 meters per second. What if we are using the biker or the kids as the reference frame or as an observer? Then, from his perspective, it seems like The person who's standing still is actually moving back. So relative velocity of the person relative to the biker would be VP minus VB. 0 minus 3, so that's negative 3 meters per second. And here, a negative sign means that they're moving towards the negative direction, which is towards the left. Velocity is not absolute, and depending on different observer, the relative velocity can be different numbers. And as I just showed you, when you switch between the object and observer, their relative velocity would be the opposite. So VAB is negative of VBA. For example, when the kid was moving to the right, its velocity of can be represented as VB. And as I said before, VB is actually the same as velocity of the bike relative to the ground. When not specified, we are going to automatically take the ground or the earth as the reference frame. This is 3.0 meters per second. From this kid's perspective, the ground is actually moving at negative 3 meters per second. This is how it looks from his perspective. Now we're going to make it a little bit more complicated. What if there are multiple objects moving at the same time? We can always use VAB is equal to VA minus VB to calculate relative velocity. And again, here VA means VA relative to the ground, VB relative to the ground. And if we rewrite that, then we get that VA relative to the ground is equal to VAB plus VBG. How I think of it usually is when you add up to velocity, make sure that these two letters inside are the same and they can be canceled. So now I'm going to take A and G. So VAB plus VBG becomes VAG. So here, for example, there are two objects moving. If I want to calculate how fast the car was moving relative to the bike, then I can represent that as V car relative to the bike. And this can be written as V car relative to the ground plus V ground relative to the bike. Let's say the car was moving at 6 meters per second to the right, while the bike was moving at 3.0 meters per second to the right. Then for VCG, I can just plug in 6.0 meters per second. For VGB, since this is the velocity of the bike relative to the ground, so for VGB, I'm going to take the negative value. So they add up to 3.0 meters per second. This means that when the kid looks at the car, he sees the car as moving to the right at 3 meters per second instead of 6 meters per second. So, in the previous example, we were talking about relative velocity when two objects were moving in the same direction or when they're moving along one single line. But often in reality, what happens is we need to calculate relative velocity in two-dimension setting, not just one dimension. So here is an example. You are driving a boat trying to cross the river, and the river is moving towards the right. Here, the boat is pointing right up. This is actually velocity of the boat relative to the river. So this is VBR. And at the same time, the river is moving towards the right. So this is V river relative to the ground. Let's say there is an observer standing at the shore. I'm standing still right there. Then from his perspective, the boat is moving at VB relative to the ground. And this can be calculated using this formula as VBR plus VRG. And we've already learned the vector addition. And this time, these two vectors, VBR and VRG, are not pointing in the same direction or opposite direction. So just using tail-to-tip method, VBG will be pointing from this point to this point. Now, let's try to solve some questions related to relative velocity. Two trains approach each other with the same speed of 50 kilometers per hour. What is the velocity of the yellow train relative to the red train? The first step I'm going to do is take one of the direction as positive, and then I'm going to convert all this speed into velocity. So velocity of this yellow train relative to the ground would be positive 50 kilometers per hour. For this red train, its velocity relative to the ground would be negative 50. If I just translate this to variable, that's v yellow red. Based on the relative velocity formula, this would be vyg plus vgr. We already have vyg, which is 50. For vgr, we do not have that yet. But we know that vrg is negative 50. And we know that if you switch those two objects, so one becomes observed, the other one becomes the reference frame, then you will have to switch the sign. So I'm going to make negative 50 into positive 50. And then I'm going to plug that in. The velocity of yellow train relative to the red train would be positive 100 kilometers per hour. Next, it's the same question, but this time there is a fly flying to the left at 75 kilometers per hour relative to the yellow train. My first step would be taking one of the direction as positive direction. My next step would be labeling all of the known velocity. And for the fly, its velocity will be represented as VFY to negative 70 kilometers per hour. And now let's try to represent what we need to find using variable. Velocity of the fly relative to the ground. So it should be VFG. And using the relative velocity formulas, VFY plus VYG. VFY is negative 70. VYG is positive 50. Next, let's try to find the fly's velocity relative to the red train. VF relative to R. VFG plus VGR. VFG is negative 25. We are not given VGR, but we are given VRG. When the observed object and the reference frame are flipped, it will be positive 50 kilometers per hour. So negative 25 plus positive 50 is positive 25 kilometers per hour. Next question. Plane A flies at 500 miles per hour, 30 degrees south of east. This is 30 degrees. And plane B flies at 600 miles per hour due north. What is the velocity of plane B relative to plane A? First off, let me try to represent all those arrows in terms of relative velocity. It's asking us to find the velocity of plane B relative to plane A. And using the relative velocity formula, it should be VBG plus VGA. VGA would be negative of VAG. For a negative vector, it would be pointing in the opposite direction with the same magnitude. So this would be VGA. We can add up these two vectors to get the vectors VBA. What we are going to do in vector addition would be breaking it down into x component and y component and add up all the x components and add up all the y components. For VGA, its x component would be 500 miles per hour multiplied by cosine 30 degree, 433. And its y component would be 500 miles per hour multiplied by sine 30 degree, 250 miles per hour. So eventually, for the resultant vector, its x component would be 433 miles per hour. The y component would be 600 plus 250, 850 miles per hour. We are going to use Pythagorean theorem, and we're going to calculate the square of 433 plus square of 850, and then add them up together, and then we take a square root on that sum. 954 miles per hour. And we can calculate the angle right here by taking arctangent of the x component and y component. Then the velocity of plane B relative to plane A would be 954 miles per hour at whatever this angle, let's say it's theta degree west of north. Next question. Two trains are moving towards each other at the labeled speed. Two men are running at the labeled speeds relative to each train. For the blue man, he's running at 20 kilometers per hour relative to the blue train, and the red man is running at 15 kilometers per hour relative to the red train. And what is the velocity of the blue man relative to the red man? First off, you need to know that there are four objects that are moving and we have ground. So you can think of there are five objects in total. I'm going to use capital letter B to represent blue man, capital letter R to represent the red man. And I'm going to use the lowercase b to represent the blue train and lowercase r to represent the red train. Then eventually what we need to find would be velocity of capital B relative to capital R. This can be written as velocity of blue man relative to ground plus velocity of ground relative to the red man. Now let's take a look at the blue train and the blue man. Again, I'm going to convert all of these given speed into relative velocity. So this means V blue man relative to ground is equal to V blue man relative to blue train plus V blue train relative to the ground. That is 100 kilometers per hour. We already found it. And next, let's try to find the velocity of the ground relative to the red man. Velocity of the red man relative to the ground is equal to VR small r plus V small r plus G. Negative 15 plus negative 60. So that's negative 75 kilometers per hour. And I'm going to convert that into VGR, which is positive 75 kilometers per hour. Now I have VGR. So it's 175 kilometers per hour eventually. This question is not a mathematical question. You're not required to do any math. A truck is moving at a constant velocity of 5 meters per second, and a person throws a ball straight out from the truck. Okay, where will the ball land? Will the ball, after a while, when the ball land, will it land behind a truck, inside a truck, or in front of the truck? So, this is a really easy question if you understand what it means by reference frame and relative velocity. I'm going to take the truck as the reference frame. If the truck was not moving, then the ball will just go straight up and straight down and it will land back to the person's hand. And that's exactly what's going to happen when the truck is moving at constant velocity. What you will see as an observer standing still on the ground is the ball is moving like this. It will land back inside truck.